All right, let's get straight to it. If you're gearing up for a big chemistry exam, WAEC, JAMB, NECO, then you are in exactly the right place. Today we're going to crack the code on the single most powerful tool you have. We're going to turn that periodic table from just a confusing chart into your personal key for absolutely acing those exams. So let me just ask you this straight up. I want you to think about all the stuff you're studying, your notes, your textbooks, everything. What is the one thing that holds all the secrets, the key to predicting how elements are going to behave? It's not your calculator, even though that's pretty useful. It's the periodic table. And I want you to stop thinking of it as a list and start seeing it as a roadmap, maybe even a secret code. Because once you learn how to read it, the answers to so many questions just pop right out. So let's start decoding our map. Okay, so to read any map, you have to know the rules of the road, right? That's what periodic trends are. These are the basic patterns that control every single element on there. Get these down and you're halfway there. This slide really gets to the heart of it. Let's just take atomic radius, the size of an atom. As you move from left to right across the table, you're adding more protons to the center. That stronger positive charge literally yanks the electrons in tighter, so the atom actually shrinks. But when you move down a group, you're adding whole new layers, whole new electron shells, and that, of course, makes the atom bigger. It's this simple push and pull that explains pretty much every other trend you see. But here's the catch. This is where the exam writers love to try and trip you up. See, these trends aren't perfect straight lines. They've got bumps, exceptions. And knowing these little exceptions, that's what separates a good score from a truly great one. And here it is. This is a classic exam trap, beautifully laid out. You'd expect the energy needed to remove an electron, the ionization energy, to go up as we move from beryllium to boron. But look, it actually drops. So why? Well, beryllium has a full, super stable outer shell. It does not want to give up an electron. Boron, on the other hand, has this one lonely electron sitting in a slightly higher energy shell. It's further out, it's easier to grab, so it takes less energy to pluck it off. Understanding this little detail is pure gold for your exams. So let's move on and see how all this connects. If the rows in our map are periods, then the columns, the groups, are like families. And just like real families, all the elements in the same group, well, they share similar traits and personalities. And the best part is, this makes them predictable. Look at the alkaline metals in group 1. They all have just one single electron in their outer shell that they are desperate to get rid of. That's why sodium goes absolutely wild when you drop it in water. Then all the way over on the other side, you have the halogens in group 17. They're just one electron away from having a full shell, which makes them super aggressive about taking an electron from someone else. And the transition metals in the middle, they are famous for making these gorgeous, colorful compounds, like that vibrant blue color of copper sulfate in water. Okay, so we know the trends and we've met the families. Now let's see how these elements actually, interact. This is where we get to the real heart of chemistry, bonding and reactions. And guess what? It all comes right back to the periodic table. When a super reactive metal from the left side, like sodium, meets a super reactive non-metal from the right side, like chlorine, it's not a negotiation, it's a transfer. The metal gives away its electron, the non-metal takes it, and bam, they form a really strong ionic bond. But if two non-metals get together, they both want electrons, so they have to work out a deal. They share them, and that forms a covalent bond. Now, what if you want to break that strong ionic bond? This is a huge topic, especially for the NECO exams, so listen up. The process is called electrolysis, and it's basically just using electricity as a hammer to smash a compound back into its original elements. Let's picture molten table salt, NaCl. The positive sodium ion is a cation, and you can remember that because the T looks like a plus sign. It's drawn to the negative electrode, the cathode. The negative chloride ion is an anion. It's drawn to the positive electrode, the anode. The biggest mistake people make is mixing these up, so just burn this into your brain. Anions go to the anode, and cations go to the cathode. Simple as that. All right, theory is great, but let's put our new code-breaking skills to the test. We're going to tackle a real question from a past exam. This is how you turn what you know into actual marks on the page. Hey, does this look familiar? It should. We literally just talked about this. This is a perfect example of how examiners check if you really understand this stuff, not just if you've memorized it. So let's break down the perfect answer step by step. Okay, the very first thing you should always do is write out the electron configurations. It immediately shows you what's going on. Look at beryllium. Its outer shell, 2s2, is full. That's a stable, happy atom. Now look at boron. It has that one extra electron hanging out in the 2p1 subshell. Not only is it in a higher energy level, it's also shielded by the other electrons, which means it feels less of a pull from the nucleus. That makes it way easier to remove. And there it is, the trap. Laid bare. If you just memorize ionization energy increases across a period, you would get this question wrong. The key takeaway, the deeper understanding they're looking for, is that the stability of these little subshells can actually override the general trend. So if you had to boil it all down into one perfect sentence for your exam, it's this. Boron's outermost electron is in a higher energy, shielded p orbital, making it less tightly held and easier to remove than an electron from beryllium's stable, full s orbital. That's simple, it's precise, and it's a guaranteed mark. Whew. Okay, we've covered a ton of ground. So before we wrap this up, let's just condense everything down into a quick, powerful summary. Think of this as your ultimate cheat sheet for using the periodic table to win on exam day. Here are the absolute must-notes. Number 1, master the main trends across and down. Number 2, know your families, especially the alkali metals, the halogens, and the transition metals. Number 3, if you're taking NECO, you have to be flawless at balancing equations. Number 4, for JAMB, be on the lookout for those trend exceptions we talked about. They love asking about them. And finally, just memorize a few key facts, like the color change of copper sulfate from white to blue when it gets wet. Those are easy points you just can't afford to miss. So what's the big idea here? The periodic table is not something you memorize. It's a tool you have to understand and use. So to leave you with something to think about, here's a little practice question. We know it happens in electrolysis, but what affects how fast it happens? Think about it. The answer comes from applying the same principles we've covered today. Thanks for tuning in, and seriously, good luck with your studies. That's it for today. Great job following along. If you found this tutorial helpful, don't forget to subscribe to our YouTube channel for more easy-to-understand lessons. And hey, want to practice more questions and get step-by-step solutions? Visit examkp.com right now and keep learning smarter.